Tonight's talk, Exploring the Solar System with the James Webb Space Telescope by Heidi Hammel of Aura. I'm Dr. Frank Summers, your host from the Office of Public Outreach at the Space Telescope Science Institute. And as always, I want to thank our wonderful tech team, Gary Gilbert and Grant Justice, who help us get this out to you and out to the audience on YouTube. So our upcoming talks, well, as you might remember, that funding for the public lecture series went away in the fall quarter of 2024. We were able to finish out 2024, but we had to take a short hiatus in January while we try to, figure out what's going on and come up with ideas and everything. And there is new funding for 4 events in fiscal year 2025. This one, plus there's going to be one in April, June, and August. Those are all to be determined because, well, we're going through a whole lot of changes right now, okay? And the biggest change that's going to happen next month is that you are watching this probably on the Hubble Space Telescope YouTube channel. But due to funding changes and the changes in our Hubble funding, the Hubble Space Telescope YouTube channel is going to be shut down by the end of March 2025, okay? Don't worry, we still got you. I mean, Hubble don't got you, but we still got you. Space Telescope got you. We will have all of the public lecture series content on the Space Telescope Science Institute channel. Okay, so whereas you used to go to youtube.com/Hubble Space Telescope, you now go to youtube.com/Space Telescope Vision. Okay. And you will find our STSCI channel and hit that subscribe button. Okay, we do not want to lose you as a viewer. We want you to change your subscription from HST over to STSCI, and you'll still get the same great content over there. I'll just have a different channel name. Okay. There are also a couple more changes that's happening. We're going to change the name of the event. It's going to go from public lecture series to some new name. Okay, there was a brainstorming session the other day, and about 25 different names were postulated. Okay, so they have yet to choose it. Okay, but there's going to be a new name that will be determined, and there will be some small format adjustments on ways that we can get it out to you better to think. But let me guarantee you, what's not changing is we will have the same great content. We will have astronomy experts talking about the science they know and love directly to the public. Okay, that's been the heart of this for the 22 and a half years that I've been hosting it. Okay, so yes, that will stay the same. All right. Okay. Well, if you want to find out what the April, June, and August ones are, you can go to stsci.edu/public-lectures. And well, yeah, I just told you that the name is changing, so this page will look differently, but don't worry, we'll do a redirect. If you go to that link, it'll redirect to the new page, okay? Don't worry about it, all right? And again, always on that page, you can find our webcasts both on our YouTube playlist and on our webcast archive. And that YouTube playlist will, of course, be on our new YouTube channel. All right, so there's just a lot of things that we got to accomplish over the next month after we finish here tonight. Okay, you might want to sign up for the emails because that will help you get the new information. Okay, during this process of change. All right, and so the communications. I've already talked about the announcements. Sign up the website. I've already talked about the YouTube channel. Subscribe to that. Finally, the last one is that if you have comments or questions, you can send them to publiclecture@stsci.edu, okay? And we will be able to get back to you. The other way you can follow us is, of course, on social media. And we are no longer doing social media for the Hubble Space Telescope. That's part of the changes that we're undergoing. But we are still doing it for the Space Telescope Science Institute and some of it for the Webb Space Telescope. So we're on Facebook, we're on X, we're on Instagram, and I haven't mentioned this before, we are on Blue Sky. Okay, so if you want to follow us on Blue Sky, and of course we are on YouTube. All right, so lots and lots of ways to find about what's going on. I know there's going to be some changes, and I just please take the effort and follow us so that you can find out about how things change. Okay, now the news from the universe for February 2025. My first story, Mr. Andromeda's Neighborhood. And yes, that's a playoff on Mr. Rogers' Neighborhood, which I watched when I was a kid, and my kids watched when they were growing up. But this is a different type of story here. Okay. So, this is an all-sky view of our Milky Way. You can see the band of our Milky Way stretching across the sky. And one of the interesting things you can see in this image is these two clouds right there. Okay, let me blow those up for you. These are what's called the Magellanic Clouds. This is the clouds in the sky that Magellan saw on his trip around the world way back when. And it's sort of like he discovered them. Well, no, he didn't discover them. They'd been seen forever from people in the southern hemisphere, but he brought the knowledge of them back to Europe. Well, actually, he didn't because he didn't make it all the way through. But don't worry about that. Anyways, they get called the Magellanic Clouds, okay? And we have a small Magellanic Cloud and a large Magellanic Cloud. Hey, we astronomers are pretty creative. We got pretty basic when we're describing things, okay? And these are satellite galaxies around our Milky Way, okay? And if I go back to that Milky Way image, there's not that many other of these satellite galaxies. If you look really, really hard with telescopes and everything, you can find about a dozen satellite galaxies around here. But what I've got circled here is actually another interesting object, but it's not a satellite galaxy. It's its own galaxy, the Andromeda Galaxy, also known as Messier 31. And when you look at M31, it's pretty obvious that it has a couple satellite galaxies of its own. The two bright ones that are right near the main part of the Andromeda are M32 and NGC 205. So you can see it's got two bright ones. So it's kind of like the Milky Way, right? No, actually, it's got a lot more of these satellite dwarf galaxies around it than the Milky Way does. And so here is a image of the Andromeda. You can see how small Andromeda is here in the center. And all of those orange circles are dwarf galaxies around the Andromeda Galaxy. It has about 3 dozen. Okay, and these satellite galaxies were the subject of a recent study from the Hubble Space Telescope. And so we want to give you a feel for just how many and their distribution. So here is a video exploring them in 3D. All right, so you've got these big panoply of galaxies around Andromeda. What does that actually tell us? Well, by studying the dynamics and the kinematics of these satellite galaxies, we actually learn that the history of Andromeda has been much more rough, a lot more interactions. They believe there might have even been a significant merger a few billion years ago, where compared to the satellites around the Milky Way and the small number of them, they find that, not much is happening. It's relatively quiet. Okay, so when we looked into Mr. Andromeda's neighborhood, we found that it's a bit rougher of a neighborhood, at least galaxy kinematic dwarf galaxy wise, than it is the neighborhood around the Milky Way. My second story tonight, echoes of a distant boom, and this takes place in the constellation of Cassiopeia, or as I like to refer to it as the W constellation, okay? Because it's up there in the northern part of the sky, and it's a nice little W, very easy to find. I actually use Cassiopeia, the stars in it, to help me find the Andromeda galaxy where it is, because it's actually Andromeda's just to this, just below it in this image, just off the screen here. But what I want to talk about here is not Andromeda yet again, but something in Cassiopeia right there. All right, can you see it? No, you can't, because it was discovered in radio waves. Okay, so this is a radio image of what's called Cassiopeia A. It is one of the brightest radio sources in the entire night sky. And what is it? It is a supernova remnant, a star that exploded, okay, in probably around 1660, that we would have seen the first light from this explosion reach Earth, except that nobody actually saw it. We can see the evidence that this exploded around that time, but we don't have any actual astronomers who saw it. Some people may have seen it, but no, it's something that was 360 years ago. We missed it. Okay, all right. Bad observing. But because it's an explosion of an entire star, it's got a huge amount of energy, and it looks absolutely gorgeous when you view it in X-rays. This is from the Chandra X-ray Observatory. All this hot gas that's blowing out and moving at 10,000 miles per 10,000 kilometers per second, millions of miles, 10 million miles an hour, um, is just energizing things, and they are so energetic they show up in X-rays. Now, Hubble and Webb have looked at Cas A as well, but they're not quite as exciting, okay? Because they're just getting the outer parts of it that are cooled down to thousands or hundreds of degrees in temperature. All right, but the story I want to tell you about here today actually goes back to a different space telescope, the Spitzer Space Telescope, and it looked in infrared. And so you can see the bright spot in the center of this image. That is Cassiopeia A. And what Spitzer does, it has a much wider field of view than either Hubble or Webb, and can take much larger fields of view. And it shows you all the dust in the region around Cassiopeia A, right? And what they did with Spitzer is they looked for the light of the supernova expanding across this space, hitting some of this dust, and then echoing towards us. Okay? We call this a light echo. Yeah, yeah. You're seeing the light from that supernova. It goes across space, hits some of the dust, and then comes toward us. All right. And so there's a time delay on it, and that we get to see what's going on here. Well, Spitzer did this successfully, and in looking at the infrared, so Webb can do it even better, and Webb can get the incredible resolution that Spitzer never could. Okay, so this is the Webb image of the Cassiopeia A, and here are two regions way across here. You see how far away it is from the supernova, um, that we're seeing light echoes today. All right, so here is the three images of the light echo from August, mid-September, and late September last year. Now, unfortunately, these images aren't aligned. They were, taken at three different times, and they aren't perfectly aligned, so you can't really see what's going on. So to do this, we have to show you a movie. All right. So this is going to just go use the time lapse and go from 1 to 2 to 3, and then it'll repeat 1 to 2 to 3. Okay, and you can watch as the light echo progresses. All right, it's kind of subtle. Look carefully. Watch it as the light echo progresses. Right now, when you watch it, you look at it and you go, "Oh, the gas is just the dust is just moving through space." No, no, no. The dust is not moving. It's the light that's moving through the dust, illuminating different parts of the dust. Okay, so I'm going to play it for you one more time. All right. Watch it as it moves. Okay, one last time. Goes to the August, mid-September, and late September. And what you're seeing is the light moving through the dust. This is light from a supernova explosion 360 years ago that we're able to see today. Yeah, astronomy is just a really cool subject, okay? We get some really cool stuff to study out there. All right, and speaking of cool stuff, our speaker tonight is going to tell you all about some amazing cool stuff. Heidi Hammel is, well, if you're an astronomer, you know Heidi Hammel, okay? She's infamous, all these things. She got her undergraduate degree at MIT and her PhD at the University of Hawaii. She has worked at a who's who of places in astronomy. She's worked at JPL, MIT, the Space Science Institute in Boulder, where she worked for, that was like your longest, like 13 years, you say, right? Okay. And she's now working at Aura, the Associated Universities for Research in Astronomy, as their VP of Science. And for those of you who don't know, Aura is the parent company of the Space Telescope Science Institute. So she's like way up in the org chart, way above me. Okay. So, I got to make sure that her talk is absolutely wonderful, right? Um, and it will be because beyond doing some amazing solar system research herself, she has been an incredible presenter of science to the public. She's earned the Sagan Medal, the San Francisco Exploratorium Award, and she most recently got the NASA Medal for Exceptional Public Service. Okay, so not to build her up, that like this is put pressure on her, but yeah, she's got the track record to prove it. And one last thing is that she told me that her mom is watching. So, hi, mom. Okay. Uh, I'm going to stop talking. And here's your daughter, Dr. Heidi Hammel.
Thank you so much. I really am enjoying listening to you and enjoying being here. And let's talk about the James Webb Space Telescope. And start my presentation for you. I'm going to be talking about exploring the solar system with the James Webb Space Telescope. And what you see on the screen here is just a panoply of pictures of solar system objects with James Webb Space Telescope. But before I start talking about JWST, we need to talk a little bit about some background science so that we're all on the same page. And I'm going to start with Isaac Newton and light. Isaac Newton was the fellow who put a prism in front of a pinhole camera or pinhole in the wall and used that prism to spread the light out into its rainbow of colors you can see in this picture from red to blue. But the light doesn't stop at red and it doesn't stop at blue. Light continues onward into what we call the full electromagnetic spectrum. And we can only see the visible part, but there are other kinds of light out there in the universe, such as ultraviolet light, X-rays, microwaves. You've heard of some of those things because you use light in your microwave oven. And if you've ever broken a bone, you've used X-ray light to take a picture of the bones inside your body. But astronomers care about all of these wavelengths, not just the visible wavelengths. And that's because the universe emits light at all of these wavelengths. In the presentation you heard from Frank, he talked about Chandra and the X-ray light that it is sensitive to, Spitzer, which was sensitive to infrared light. We want telescopes that cover that full electromagnetic spectrum because that's the way we can study the universe in its whole. And so we have telescopes on the ground, we have telescopes in space. Some of them are radio telescopes, some are X-ray telescopes. And we need to go from the ground to the space because not all light gets to the ground. So the telescope we're going to be focusing on here is the James Webb Space Telescope. You can see its icon right between optical and infrared there. And I'm going to be talking a lot about mid-infrared, near-infrared, visible, because those are the wavelengths that JWST is sensitive to. So why should we care about infrared light? Well, we can learn a lot of interesting things from infrared light. So for those of you who have been outside recently, Orion is a constellation that is visible right now. And that's a visible wavelength image I'm showing there. It doesn't have the blue lines in the sky, but most people are familiar with the belt of Orion and the four stars that make the shoulders and the knees. But Orion in the visible is really kind of plain. And I say that because when I show you this Orion constellation in infrared light, you see all the dust that you couldn't see at visible wavelengths. So that's the same constellation at infrared light. And the Orion Nebula, a place where stars are being born, totally outshines all the other stars in that area. And so Orion is a beautiful constellation. JWST will be looking at it, but I'm not going to talk about that because that's not in our solar system. But it shows you the power of infrared light. Here's another example a little closer to my subject area. Here's a beautiful Hubble image in the visible of the planet Jupiter. This isn't one of my images, although I have taken many Hubble pictures of Jupiter in my career. But when we looked at Jupiter with the Gemini Observatory, which is an infrared telescope, this is what Jupiter looks like. And these were taken near the same time. So you can see the difference, how the great red spot is essentially a hole in the infrared light. There are places where the things are very bright, but they tend to be bright in the infrared that are dark and visible. And that is telling us different altitudes. And we'll get back to this when we talk about JWST and its infrared capability. Now, JWST's superpower is actually not imaging. I know y'all like the images, and I love them too, but spectroscopy is the superpower. What is spectroscopy? This is crucial for any JWST presentation. When we look at the range of light from an object, certain materials in that object can absorb specific wavelengths of light. They just take them out of the spectrum. They're gone, they're missing. Other materials, depending on their pressure, their temperature, and other physical parameters, can actually add light to the spectrum. And these lines, we call them spectral lines, are like fingerprints for atoms and molecules and compounds out there in space. And back in the olden days, when we started doing astronomy, we did not have color printers. We did not have color displays like this. So the way we represented spectra is we would draw kind of a line across here, and where things were dark, the line went down, and where things were bright, the line went up. And so the squiggly line that you see at the bottom, and that's a technical NASA term, a NASA squiggly line chart, that is what we call a spectrum. And we look at those patterns of dips or peaks. That is what tells us the actual physical science of things out there in space. Here's an example. This is a beautiful image of something called Eta Carina. It is a massive star that is exploding. And this is a beautiful picture of it, imaged by Hubble. But when we use a spectrometer on Hubble, we put a slit there, just like Newton did with his prism and pinhole, and we spread that light out into its colors, you'll see there's bright lines there. Those bright lines we can identify based on their particular color and pattern as helium, argon, iron, nickel. And you can even see some of the lines have little shapes to them. They aren't exactly up and down. That tells us the motion of the gases and dust and other things that are causing those lines. So from a spectrum, we can learn composition, we can learn temperature, pressure, dynamics, all sorts of interesting science about things out there in the universe. And that's why spectroscopy like this is the superpower of JWST. It does this incredibly well. Now, we're now going to talk about something called redshift. When you look at a nearby star, you see a pattern of lines that is represented here with these Greek letters, alpha, beta, gamma, delta, epsilon. But when you look at a star that's a little further away, like stars in a nearby galaxy, if you look carefully, all the lines are all shifted a little bit to the red. And if you go to an even more distant galaxy, now that redshift is quite evident. And the really, really distant galaxies, those lines are shifted all the way out of the visible and into the infrared. The reason this is important for JWST is that JWST was designed to see the most distant galaxies in the universe, the oldest galaxies, the ones most far away from us. And as you can see in this cartoon, the light from those galaxies is in the infrared. And that is why everything about James Webb Space Telescope is designed to optimize the infrared. So in this cartoon that shows JWST in comparison with Hubble, you can notice a couple of things. You notice the gold mirror, all right? Why is it gold? Not because it looks pretty, which it does, but it's gold because that's a really good reflector of infrared light. And what about that big giant sun shield that you see at the bottom? That's there to keep the telescope cold because infrared light is actually heat. That's what infrared light is. And so to see the infrared light from the coldest, faintest galaxies in the universe, our telescope has to be cold too, because otherwise we're just going to see the telescope. And those sun shields are protecting the telescope from the sun, from the earth, from the moon, because those are all very warm. And so everything about this telescope is specifically designed to be a good infrared telescope. So it's designed to see the light from the first galaxies. That's the whole reason we built this telescope. But if your telescope is powerful enough to see the first galaxies, you can see other galaxies too, nearby ones and medium distance ones. And you can in fact look at how galaxies evolve over time in the whole universe, because you can see all the galaxies between now and when the universe first formed. And you can also, with this powerful telescope, look at the birth of stars and look at the birth of planetary systems. And with this powerful telescope, you can study planetary systems and the origins of life. And when I first learned about James Webb Space Telescope, it wasn't even called that then. It was called the Next Generation Space Telescope. I had been using Hubble to do solar system work, and I'm like, wow, this new telescope they're building to look for the first galaxies is going to do amazing solar system science. And so I decided I was going to do that. I was going to make sure that this telescope did that. What can we see in our solar system? If this is sort of a cartoon of our solar system, JWST is near Earth. It's between Earth and Mars. You see a little icon just popped up there. And it's got the big sun shield that blocks the Earth and the moon and the sun, and therefore it blocks Venus and Mercury too. So everything in the red, we will never look at with JWST. But that leaves a whole lot of solar system to study. And so back in 2002, it's a picture of me at that time when I was very young and very, enthusiastic. I decided I was going to write a proposal to NASA to use what was then called the Next Generation Space Telescope to study our solar system. And they took it. My proposal was accepted by NASA in 2003, and I was selected to become a JWST interdisciplinary scientist. What that meant was I had the authority to use any instrument on this telescope to do the science that I was proposing to do. And when you became an interdisciplinary scientist, an IDS, there were 6 of us, you were guaranteed 100 hours of JWST time to do whatever you wanted, as long as you didn't break the telescope. More on that later. And this is called guaranteed time observations, GTO time. So if you see GTO, I'm talking about the guaranteed time that I was granted by NASA when my proposal was selected in 2003. Now, I couldn't do this by myself. I had a great team. And I just want to acknowledge them, show them, and you can read under their names some of the diversity of things we were planning to do with our solar system time, my 100 hours of guaranteed time. I split it across the whole solar system from near Earth asteroids, that's what Christina was focusing on, all the way through to the edge of the solar system where Kuiper belt objects are, and everything in between. But these people on the screen are really the heroes of the story because they're the ones that did the real work. I just was a cheerleader for them and an advisor. My GTO team, my Guaranteed Time Observing team, designed a robust solar system sampler where we looked at all of the things that we could look at in the solar system. And we were supplemented by other GTO programs, other instrument teams. There was an early release science Jupiter team, and then the general observer. Those are just the regular rank and file astronomers who want to use JWST. They want to do solar system stuff too. And to give you a sense of how much time is spent doing solar system, this was the requests that we got for the 4th cycle of JWST solar system time. It was record breaking. We got thousands, literally thousands of proposals. Only a 10th of them will be able to be fit into the schedule. But these little blocks here on the left is how many hours were requested. On the right is how many proposals were requested. The triangles that I highlighted are the solar system proposals. And you can see that our time is small, relatively speaking, compared to the number of things we're requesting, because solar system objects, they're pretty bright. They're bright compared to like the most distant galaxies in the universe. So we don't need a lot of time to do really great science. And of that time, I wanted to emphasize for you that 68% of it is requesting spectroscopy, and only 32% of it is requesting imaging. And that's because, as I said, the spectroscopy is truly the superpower here. Okay, so let me move on. So I'm going to break this talk up into sort of 5 topics and then a conclusion. I'm going to talk about JWST looking at bright things, fast-moving things, dynamic things, 3-dimensional things, and even a 4th dimension of time. And then what I call distant in quotes, because, you know, distant in the solar system means the edge of the solar system. It's distant for us. But when you compare it to like the most distant galaxies, it's like, it's not really distant, it's local. So distant for us. So let's talk about bright things. One of the brightest objects out there in the sky, Jupiter. And this is a gorgeous Jupiter image taken by the ERS team, the early release science team, processed by Judy Schmidt. And it's an infrared image, which is why it doesn't look like our Hubble images or other visible wavelength images. One thing I want to zoom in on is up here in the north and also in the south, you can see beautiful auroral emission. And notice how this auroral emission, which is highlighted in red in this color composite, sticks up above the limb of Jupiter, above the cloud tops of Jupiter. That's interesting. One of the most surprising things the first surprise that came from JWST in the solar system was when we looked at this edge of Jupiter. You see how there's like a bright line along the edge? That's supposed to be in shadow. But there's a bright emission going on there. It's supposed to be shadowed and dark. And so there was a lot of head scratching. Well, what could this be? And we think, we have a lot of different theories about it, but we're kind of converging on it's an ionospheric glow that is all around this planet, but we can only see it here because that part is supposed to be very, very dark. And JWST is so sensitive, it could pick up this ionospheric glow. You know, we've sent a lot of spacecraft to Jupiter. We've been orbiting Jupiter with the Galileo mission. We never saw this before. And so people ask me sometimes, why do you need to use JWST when you've already sent missions to these places? This is why. We make new discoveries because of the sensitivity that JWST has. Here's a close-up of the Great Red Spot. And there's a team that is analyzing a whole lot of images of the Great Red Spot to try to understand the 3-dimensional structure from deep in the atmosphere all the way up to the top of the atmosphere by looking at different infrared wavelengths. Why is it white? Because this is an infrared image. It's not a visible image. And so we're just coloring it this color because things that are reflecting in infrared light here are high altitude. And so anything white here is a high altitude cloud. And so just by looking at this picture, I can tell you without doing any math that the Great Red Spot is covered with high altitude clouds. There's a lot of other high altitude clouds here as well. I did want to do one little zoom out because one of the most remarkable things about JWST is its incredible dynamic range. We can see things in a single image that have a full dynamic range of 1,000,000. And how do we know this? Here's a picture, a single frame of two images of Jupiter, where you can see Jupiter, and right next to it, you see its rings. Jupiter has rings. So for those of you who didn't know that, Saturn is not the only ringed planet. Jupiter has rings, Uranus has rings, Neptune has rings. But these rings of Jupiter are 1,000,000 times fainter than the planet. And yet we can see them in the JWST images with the planet. And that is some pretty amazing dynamic range. So another science result that came out from these Jupiter images. This inset here is a blow up of the equatorial region where my colleague Ricardo Hueso and other folks measured these bright clouds that you can see in some of the boxes tracking through a series of images. And they were able to map out wind speeds. And if you look over at the chart on the far right, you see there is an orange spike right at the equator, just south of the equator. And that is a high-speed jet that had never been detected before. And JWST was able to pick it up because it had sensitivity to these discrete clouds and could map them as a function of time and make a new discovery that Cassini had not seen, Galileo had not seen, Hubble had not seen, but JWST with its infrared capability was able to see. So great science. I did mention spectroscopy. These are actual real spectra of Jupiter and Saturn with the James Webb Space Telescope. And every single wiggle that you see in those spectra are actual signatures of molecules in the atmosphere. Some of them are labeled like phosphine, ammonia, methane. But there's stuff in there that is much more subtle and much more challenging, ethane, acetylene. And these look like laboratory spectra. These look like theoretical spectra because JWST is just that good. And so the team is really busy analyzing such kinds of spectroscopy to understand how these molecules vary as a function on the latitude and longitude on the planet and is related to cloud structure, both for Jupiter and Saturn. And I'll come back to the Saturn one a little bit later in this talk. Another extremely bright object is Mars. And Mars was so bright, it was very hard for us to actually find parts that weren't completely saturated, that didn't like fill up the detectors with so much light. The picture on the left is not an image, it's a map. It's a map there to show you certain geographical features on Mars. But the image in the middle is a near-infrared image with JWST, and the image on the right is another near-infrared at a slightly longer wavelength. The big yellow splotch there is warm surface, and the cooler stuff is purple. The subsolar point, like where the sunlight is beating down on Mars, is warm, and then it cools off near the limb. But you'll notice there's something called Hellas Basin there. Hellas Basin looks dark, and that you might think naively that means, well, that must be colder, right? Actually, it isn't. This is some science for you. That's a basin. That's why it's called Hellas Basin. It's a big basin on the surface of Mars, a big depression. And because it is a depression, there's more atmosphere through there. It's just you're seeing through more atmosphere before you get to the surface. And it turns out that at this wavelength of light, there's one particular spectral line for carbon dioxide, and it's extremely sensitive to pressure. And when you go to deeper pressures, like you do at the bottom of a basin, this line is actually suppressed. And so it has less light in it. And that The pressure is why it is darker there. It's not the temperature. And so you have to be very careful when you're seeing images and interpreting them. You have to think about all the science that underlies how you make spectral lines in astrophysical objects like Mars. Here's another set of spectra from Mars showing you water, which we know there's water in the atmosphere, a lot of carbon dioxide, some carbon monoxide. And one of the things that's not in this particular spectrum, but one thing we're going to be studying a lot with JWST is the molecule methane. It's a mystery molecule for Mars, Mars methane mystery. Some ground-based telescopes claim to have seen it. Our in situ spacecraft do not. Does that mean it's variable? Does that mean it comes from certain things? We don't know the answer to that. And JWST, with its remote sensing capability, may be able to give us some kind of insights into that. That's a work in progress. I don't have anything to show you about it, but it's something that I've been thinking about for a long time for Mars. So let's talk now about fast-moving things. Mars is pretty fast moving, but there are other things that move quickly. And I want to share with you a really unusual kind of object that you may not be familiar with. And that is something called a main belt comet. Now, in our solar system, between Mars and Jupiter is our asteroid belt. And it's filled with asteroids, which are basically rocks. Comets are thought generally to be things that are watery, that have some dust and gas mixed in. You've heard of Comet Halley, I'm sure. And on this chart, it shows you Comet Halley's long elliptical orbit. But there are actually 16 objects in the main asteroid belt that seem to have cometary behavior. They seem to have what we call a coma, an atmosphere of gas and dust around them. So JWST was able to track one of them, Comet 238P Reed, and it was able to measure spectroscopy of that main belt comet. And what it detected, there's a picture of it, and in the spectra, particularly the one labeled B, H2O, that is the first detection of water in a main belt comet. It had been speculated that these main belt comets had water, but we had not been able to detect it until we had the power of JWST super spectroscopy. And so this was a great result that my team member Mike Kelly published in Nature, first detection of water in a main belt comet. And you needed to track pretty fast to do a main belt comet. But the thing, I think I've told you, I mentioned at the beginning, I was allowed to do anything as long as I didn't break the telescope. Let me tell you about the observation that almost broke the telescope. And that was the observation of the Dimorphos impact in September of 2022. There was a mission that NASA created called the DART mission, the Double Asteroid Redirect Test. And this was a mission to try to move the moon of an asteroid. So the asteroid's name is Didymos. Its moon is called Didymos B, or Dimorphos. And we took a spacecraft created by the Applied Physics Lab in Maryland, and we flew it to this asteroid system, and we whacked it into the moon of this asteroid. The picture you see there is one of the last pictures the spacecraft took before it smashed into the little moon of the asteroid. And we did this because we were trying to show that we could actually change the orbit of an asteroid. And why would we care to do that? Well, maybe you've been paying attention to the news. You've been hearing about this asteroid 2024 YR4, which was discovered on Christmas Day and actually was for quite a while thought to be on a collision course with Earth. Fortunately, it's not. No need to worry. We've many more observations of it, and its orbit's been refined, and Earth is out of the danger zone. The moon is still in the danger zone. But if it had been continuing on a course to hit the Earth, we would want to deflect it, right? And so this was a test to do that. And we wanted to actually observe it with JWST. We wanted to watch the impact. And the challenge was that this asteroid pair, Didymos and Dimorphos, they were moving so fast. It was more than 3 times faster than they had told us we were ever allowed to move the telescope. And but we're like, but please, please, pretty please, can you try? So they tried, and it did track for a while, but then it lost lock and kind of drifted off. So I'm going to show you a movie of the aftermath of the impact, imaged by JWST. You'll only see kind of half a movie because, like I said, it was drifting off. And so there's the movie, and this is in the aftermath of the explosion. And so you can see how it gets bright. You can even see stuff flying off of it, like kind of down towards like maybe the 7 o'clock. You can track a boulder flying off of it. So a lot of great science has come out of this observation. Andy Rivkin on my team wrote a whole paper about the great science from watching this. And they told us, thank you for exercising the tracking capability of JWST. We will never again track that fast. And they're like, okay, we get it. Thank you very much. So now we're always going to stay within, they're actually let us go a little faster than they had promised, but not as fast as this guy went. So that was pretty dynamic, but let me show you some other things in our solar system that are dynamic that we've observed with JWST. Titan is a very large moon of the planet Saturn. It's almost like a mini world of its own. It has a very thick atmosphere, as you know, even thicker than Earth's atmosphere. And it's kind of what we could call an example of a prebiotic Earth. Its atmosphere is made of very thick hydrocarbons, ethane, acetylene, and this moon actually has a very dynamic cycle. On Earth, we would call it a hydrological cycle. You know how there's the water, we learned this in school, there's water on the ground, it evaporates, it makes the clouds rain out liquid water, which forms rivers and oceans, and that's a hydrological cycle. On Titan, the same thing happens, but not with water. It happens with hydrocarbons, methane, ethane, and weird mixtures of those things. And so what you're seeing in these images of Titan, up in the top, you see these real bright spots up in the top about like around 2 o'clock or so. Those are clouds. Those are like hydrological methane clouds, methane or acetylene clouds. And what we were able to do with a whole lot of images from James Webb Space Telescope and with the Keck Observatory, which is a large telescope on the summit of Mauna Kea in Hawaii, is many, many images of these clouds. And we're actually, over time, watching them go up in altitude and down in altitude and disappear and reappear again. And all of these clouds are all forming over what we call the Northern Lake region on Titan. This is where there are literal lakes of hydrocarbons, just ethane and methane and sort of like gasoline, lakes of gasoline on the surface of this moon. And so with all, you can see sort of a timeline in this cartoon where X's are where we don't see clouds, but the little cloud symbols are where we do see clouds, and you can see different altitudes over time. So we're actually seeing convective activity taking place on Titan. And really some very interesting science going on there. It's complemented by a whole lot of spectroscopy, which is all like blow your socks off, hydrocarbons. I'm not going to talk about that today, but it's all wonderful stuff. So that's one kind of dynamic activity, seeing clouds rise and fall above the lakes of Titan. There was another observation I made, our team made, led by Pablo Santos Sanz. And what you're seeing here is a whole series of JWST images. That's a star that is standing still. And that thing that's moving across it is an object called Chariklo. Chariklo is what we call a centaur. It's kind of like a comet, but it doesn't ever come close to the sun. It stays between Saturn and Neptune. And so we were hoping to actually measure the star when Chariklo crossed in front of it to measure the size of Chariklo. But at the like 2 weeks before our observations, the spacecraft JWST did a pointing maneuver correction, and it shifted the orbit just a little bit, and it turned out that we missed the body. But Chariklo has rings. We knew that from other occultations. So here's a cartoon of Chariklo, the body, and its rings. And the apparent star path that you're seeing in that video went just north of the body. So we didn't see the occultation of the body, but we did see the rings. And what's interesting to us is that these ring observations don't match some of the ring observations that have been made from the ground in earlier years. So does that mean that the rings are evolving? We're not sure. Does it mean that the rings maybe just are different in the infrared? Maybe. We're still working to sort that all out. We also got spectroscopy of the rings and the body together, the blended spectroscopy. We can't resolve the object. It's like a point source, but you could see tons of water ice on this object. And so it's a very interesting crystalline form of water ice, which tells us a lot about the formation of Chariklo and its rings. And so I like this. It's an homage to my mentor, Jim Elliott, who was Mr. Occultations, and I cut my teeth in astronomy on occultations. So I made sure that we did one with my guaranteed time, and that was this observation. Another very dynamic object is Enceladus. This is another moon of Saturn, and it's embedded in a blue ring. And we knew that Enceladus actually had water spewing out of its south pole. What we did not expect to see, which we saw with JWST, is that water that Cassini detected right at the South Pole actually extended for thousands of kilometers. And it was something crazy, like the equivalent of 62,000 swimming pools worth of water per second blasting out of Enceladus that we were able to image directly. And I'm going to go back, if I can. Yeah, I'm going to back. We got to go through this one more time. Hold on. Okay, now I want you to see the movie again, because when you show the zoom in of the block that is the JWST image, everything in it is blue. You can see the plume. This is the JWST image, but everything around it is blue too. That's all water. Every point in that picture, we had a spectrum that we could see water. So we now know that that blue ring around Saturn is all water coming from Enceladus. And so a really amazing, unexpectedly large, massive water plume seen with JWST. Let me talk a little bit about some three-dimensional work. We've already talked a little bit about three-dimensional stuff in Titan's atmosphere. I'm gonna show you some Neptune pictures because, of course, Neptune's one of my favorite planets. I worked on the Voyager Neptune mission. I'm still waiting for a new mission. But this is like the closest I'm going to get. My mom knows that when I saw this picture, I started to cry. And then I started to jump up and down because this is an amazing picture. The rings there we literally hadn't seen since Voyager in 1989 until this JWST picture. That's a long time to wait to see those rings again. But I'm going to talk about the atmosphere. And what I'm going to show you here is I'm going to show you a spectrum of Neptune, and it moves from reflected light to thermal light. So sunlight reflected to thermal emission from the planet. And we're going to scan through the spectrum, and you're going to see a picture of Neptune at every single wavelength. And what you will see is how the clouds that you see on the planet here change as a function of wavelength, which tells us their altitudes, and it tells us their composition. And so when you think you've seen one picture of Neptune, you have not seen them all right? So let's take a look at that. So on the bottom, I'm scanning through the wavelengths, and you're seeing the pictures change. So sometimes those clouds disappear. Sometimes they're at the pole. Sometimes you see them around the edge of the planet. And this all has to do with the three-dimensional structure of the planet. It's looping, so you can watch it a couple of times. And by moving up and down in the atmosphere, sensing different parts of the planet, what's reflected light, what is emitted light, we can take all of these data, every single one of these images, and put together a three-dimensional map of the atmosphere of Neptune using the JWST data. So we have spectra at every point on this planet, And then we can make maps of the planet as a function of wavelength. This is an incredibly powerful tool with JWST, where we can really probe with great fidelity the three-dimensional structure in the planet of Neptune. Now, I showed you this picture earlier because this was Saturn and Jupiter, and I bet you're going to ask me the same question. Can you do the same thing? It's a little harder because these are big planets, like they appear larger in the sky because they're closer than very distant Neptune. And so our field of view with JWST doesn't see the whole planet. We can only see pieces of the planet. But I'm going to show you the same thing now for Saturn as I did for Neptune, but I'm only going to do it like on the polar region and the equatorial region because that's all really we could fit in. But it's the same concept, and you will see the same thing about how the clouds are changing as a function of wavelength. I don't have the bar at the bottom, but up in the right upper right corner, there's wavelengths going, so you can see how that changes. And you can see how, now there's the pole, and then at other times it's the mid-latitudes. This has to do with where the molecules are, what altitude they're at, and what their pressures and temperatures are. So we can back out all of that information from all of these data to build up three-dimensional models of the atmospheres of these planets. And my go-to guy for outer planet work with JWST is Lee Fletcher at the University of Leicester. He and his team have done absolutely fantastic work with Jupiter, Saturn, Uranus, and Neptune. All right, we're kind of nearing the end of the solar system here. We're moving outwards, and now we're going to what I call the most distant part of the solar system, and that is what we call the Kuiper Belt. The Kuiper Belt is this whole collection of objects. You've heard of the asteroid belt? That's inside the orbit of Jupiter. The Kuiper Belt is actually outside the orbit of Neptune. That blue circle there is the orbit of Neptune. And so we often call these objects trans-Neptunian objects. You're going to see both acronyms, and I may slip up. I might call them KBOs, Kuiper Belt objects. I might call them TNOs, trans-Neptunian objects. They're all the same thing. They're all objects that are out there beyond the orbit of Neptune. Now, there's one that everyone is super familiar with, all right? And that's the one that's shown, its orbit is shown there. That's our friend right here. That is Pluto. All right, Pluto is a Kuiper Belt object. It is a trans-Neptunian object, and it's just another TNO, folks. That's where I stand on this issue. It's a pretty big one, but it is one of thousands of objects, and it is not necessarily the biggest one. Eris edges it out just a little bit, and there are a lot of other big ones like Hammel and Makemake and Quaoar, and a lot of big guys out there, and so. But this realm of distant objects is kind of the most exciting field right now for JWST because they have been so hard to study because most of them are small. I mean, the only reason we know about Pluto is because he's a big one, but there's thousands of them and they're all way smaller than Pluto. So they're really, really hard to study, but you can study them. Now, we have had one mission to the Kuiper Belt, and that it has been the New Horizons mission. And it took these two pictures, two very different Kuiper Belt objects. One is Pluto on the left. The other is Arraketh on the right, which is a really weird looking Kuiper Belt object. It's like two bodies kind of stuck together. We do actually have a third image I want to show you, which probably was a Kuiper Belt, and that is Neptune's moon Triton. We think this is a captured Kuiper Belt object. It's a twin to Pluto, except Neptune, it got too close to Neptune and Neptune captured it. And we know that because it's going in the backwards orbit around Neptune, or it couldn't have formed there. So Neptune captured that object. So Pluto, Triton, and all the big Kuiper Belt objects, they were all a major target for JWST. In fact, we actually had to set up a special committee because everybody wanted to observe them. My GTO program, Jonathan Lunine's GTO program, every instrument team wanted to look at Kuiper Belt objects. There were some other folks with GTO time, a huge, large program by Noemi Pinel Alonso and others. Everybody wanted to look at Kuiper Belt objects. So I'm going to show you some results that are really kind of hot off the press. I was just at a conference 7 weeks ago, January of this year, at the Observatoire de Paris in Meudon. And there was a whole session devoted to Kuiper Belt objects. And to give you some of the titles there, it's just a subset. There was just so much, and I learned so much about the Kuiper Belt. What we are finding is we are now starting to do rigorous statistically significant taxonomy of Kuiper Belt objects. We are discovering that there are different classes of Kuiper Belt objects. The nicknames that people are working with are called bowl, double dip, and cliff. Bowl objects, they're called bowl because if you see on the left of the, excuse me, on the right, there's a big sort of scoop shape that has H2O right in the middle of it, the one far on the right. That's the bowl. You notice in the other two ones, the orange one and the red one, you don't see that bowl. That's a water-rich Kuiper Belt object. It also has carbon dioxide, signatures of dust, silicates. 25% of the many objects. I think we're up to over 75 Kuiper Belt objects now observed. 25% of them are bowl type Kuiper Belt objects, or TNOs. Then almost half of them are what we call double dip. Double dip refers to those wild wiggles that you see between 4 and 5 microns. And these have strong carbon dioxide features, strong carbon monoxide features, a lot of organic signatures. I'm showing you sort of composite spectra here. In the next slide, I'm going to show you some insanely detailed spectra, but I just wanted to give you sort of these are like the archetypes that we're working with. And thirdly is what they call cliff. I don't quite know why they call them cliff, because the cliff there looks kind of like the cliff in double dip, but it doesn't have the double dip, so it's just the cliff. I don't know. That's what they say. But what you see here is you also see the CO2, the carbon dioxide, and the carbon monoxide, CO, but you see methanol, you see organics, you see nitriles. And what I learned at this meeting 7 weeks ago is that there are now enough samples that they are able to distinguish between a cliff 1 and a cliff 2, and then cliff 2A and cliff 2B. So we have so many observations now that we're starting to build up this taxonomy of the Kuiper Belt. And what's really important about that is it's telling us where things are forming. I told you I'd show you spectra. Here are spectra. There's so much chemistry here. One of the most exciting things about JWST and its spectroscopy is it's so good that it has blown past our ability to do laboratory measurements of many of these molecules, not only for the solar system, but for interstellar clouds and dust clouds, galaxies. We are finding lines in the spectra that we do not know what the analog is in the laboratory. So that's because it's so powerful. And so you see sometimes there's question marks when they're trying to identify things. Is maybe it's CO2, maybe it's acetylene, maybe it's ethane. The point that I want you to take away is that they are rich. What looks to you like noise is not noise. It is signal. It is chemistry. And so we are able to do this incredible chemistry in the outer solar system. And what we're learning from the chemistry, what we're learning from these archetypes that I described, the bowls, the double dips, and the cliffs, is we are figuring out where exactly things formed in the solar system. You don't see nitrogen unless you are at a certain distance from the sun in the primitive solar nebula. And you don't see carbon dioxide unless you are at a certain distance. And I'm not going to go into all the details of that because it would take a whole talk to do that. It took us a whole session at the meeting in Paris to describe all this. But I wanted to actually share with you just a little conversation that was taking place in real time at that meeting, to just give you a sense of how intrigued and excited I and my colleagues were. I was one of the note takers at the meeting. And so this is a little bit of dialogue that was written in the notes that I was having with the other note taker, Stephanie, who works with me, Stephanie Milam. And this took place 7 weeks ago at that conference. And when I saw the spectra, I wrote, for the Kuiper Belt, JWST data is now starting to get the level of complexity we're already seeing in the asteroid belt. Though if I'm following it, the arguments are that this is mostly primordial. It's telling us where things are forming It's not evolutionary. It's not where things are moving to. And Stephanie answered, yeah, kind of, yeah, but those JWST data also suggest that the radiation from the sun and from the interstellar medium is cooking or altering some of the primordial ice. And we both know that the solar and interstellar medium radiation cooks everything. But if we can disentangle this chemistry with the JWST data, that may be the insight we need to understand the evolution of the early solar system. So this is where we're at the cusp of starting to understand in pictorial form, how did we get from this early sort of dust-filled solar system that didn't have any planets in it to the system we have now. And the Kuiper Belt is the key to all of that. And not only is it the key to understanding our solar system, we are now, with our powerful tools like JWST and other ground-based tools like ALMA, we are starting to image planetary systems forming around other stars. Now, that cartoon I'm showing you in the upper left there is just an artist's concept. We weren't here to see our primitive solar nebula, but we actually have pictures of other solar systems being formed right now. And these are pictures from a telescope called ALMA, the Atacama Large Millimeter Array in the Atacama Desert in Chile. Every single one of those blocks is a planetary system in formation. And there's, you can see structures in them. And people theorize, well, that's the snow line for carbon dioxide, and that's the snow line for nitrogen-bearing species. What we're doing now with JWST is measuring those snow lines in our solar system on actual bodies. And so we will be able to use that to help pin down the formation mechanisms for these other solar systems. And that will eventually help us understand how solar systems come to be. And that will help us understand how we can find solar systems maybe like ours out there, that might have planets like ours out there, that might have the conditions for life on those planets out there. And this is all kind of just starting to come together now with the JWST data that we're getting. So it's, you can tell I was pretty excited at that meeting, like, wow, this is what you dream of. Like, you're cracking open a whole new window into planetary system formation. Okay, so bright, fast moving, dynamic, 3D, 4D, distant, and there's so much more. I haven't even talked about so many things that I could talk about. I didn't talk about Europa. I didn't talk about our new measurements of the auroral activity on Uranus and maybe Neptune. I didn't talk about Callisto. I didn't talk about rings. I didn't talk about so many things because I didn't have enough time. Here's beautiful Uranus rings, one of my favorite planets after Neptune. And maybe I didn't talk about your favorite object either. And if I didn't talk about your favorite solar system object, ask me about it in the Q&A, and I'll tell you whether or not we talked about it, whether or not we observed it with JWST and what we might have learned. So I showed this picture earlier, and I wanted to show this picture because I wanted to show you a picture 20 years later. And 20 years later, that first picture is when I wrote my proposal to get JWST with my little baby Lucas. And this is the picture of Lucas when I got my JWST data for the first time. JWST took a long time to come to fruition. And these large missions do. They take a long time. They're generational missions. And so what about the future? Okay. I am not going to show you what I'm going to look like 20 years from now because I don't know. I probably still be here, but I don't know what I'm going to be doing. But JWST could still be working. We have enough fuel on JWST to work for 20 years. That's because we got a great orbital insertion by the Ariane 5 rocket that launched us. Whether or not we will have the money to do that is another question. And so if you like what you see here and other JWST things, I invite you to write to your congressional representatives plural in Washington, and tell them that you think science is important at NASA and you want to see JWST continue. We've been hearing about getting budget cuts even now while we're in prime mission, which makes me want to cry because we're in prime mission. But if we want to finish prime and continue on, we have the fuel. We just need the funding. So it's on you to do the writing. But also in 2042, I am hoping that we actually have the next generation space telescope. And this is something that we are starting to work on now. It's called the Habitable Worlds Observatory. And the purpose of this telescope will be to take the spectrum of an Earth-like planet around a sun-like star and see in the spectrum whether or not there are the ingredients for life in the atmosphere of that world. That's the telescope we're trying to build. But remember when I told you about JWST? It was built to look for the first galaxies, but I knew it would do great solar system science. Same thing for habitable worlds. We're going to look for a living Earth around a sun-like star, but it will also do great solar system science. It's not going to be me. That's the next generation's job to do. So there's young people out there. I'm like, this is for you. This is your mission. You go and do it. I'm with you on that. So my last slide, I just wanted to have a little thought from Carl Sagan, because from my generation, he was so inspirational. And he said something that resonates with me about JWST and Habitable Worlds Observatory and all the amazing science that NASA does. He said, for all our failings, despite our limitations and fallibilities, we humans are capable of greatness. And for me, JWST is an example of the kind of greatness that we, humanity, can do when we work together. So I hope you enjoyed that whirlwind tour of the solar system with JWST. I'm going to stop sharing, and now we will probably take some questions.
You betcha we're going to take some questions. The chat has been exploding with all sorts of questions. We could keep you here for another couple hours, I think. Thank you, Heidi. That was a wonderful talk, as usual. I really wanted to emphasize your comment about spectroscopy being the superpower, okay? Because what is the percentage of observations that are being done with JWST that are just spectra? Because the public usually only thinks of the images. Do you happen to know that number?
I don't know for overall for the whole telescope, but I think it's going to be comparable to what I showed for the solar system. That fully 2/3 of the solar system request for cycle 4 is for spectroscopy, right? And I think that it's comparable. I mean, for these distant galaxies, you can't resolve them. There's little red dots. And so it's really the spectroscopy that gives you the core science. That now, don't get me wrong, there is great science to be done in the imaging as well. But the spectroscopy is what really gives us, as I said, it gives us the real meaty science, like the
Right.
actual compositions and temperatures and pressures, dynamics. That's what we need to understand things.
Right, and you're really getting at the physics of it, okay? And you showed very beautifully how much you need to understand chemistry in order to understand astronomy. And I talked about a supernova. You need to understand nuclear physics in order to understand astronomy. And that's the interconnected of all these sciences that astronomy brings about. And I really also want to emphasize your last point about Habitable Worlds Observatory is that we're not going to have little green men in spaceships arriving here. What's going to tell us if there's a possible habitable world out there is going to be spectra, right?
Absolutely. It's going to be spectroscopy. And it's not going to be something simple. Like you're not going to look at it and say methane. Like on Earth, when we look at the Earth's atmosphere, methane comes from like cow flatulence, right? It's like, but when I look at Neptune, I see methane, and I'm like, there's no cows on Neptune, right? So methane by itself is not the thing. Oxygen by itself is not the thing. Ozone by itself is not the thing. What we're going to be looking at with habitable worlds is we're going to be looking at a mixture of chemicals that cannot be produced in an equilibrium state in a planetary atmosphere. And that means that it must be being driven by something biological.
Right. So we have to understand biology in order to do astronomy. It's yet another science we have to bring in. All right. Well, the chat has had a lot of great questions. Grant has been following it closer than I have. So, Grant, you want to turn on your camera, say hi to everybody, and give us a question from the chat.
Absolutely. And yeah, chat has been great today. All right, so I'm gonna start with some more general ones and then move into heavier duty questions. First off, we have an entire program specifically about JWST that I would recommend people who are interested in the more general stuff to go watch. But what is the proposed length of the JWST mission itself?
When we crafted JWST, our nominal mission, our planned mission was 5 years. That's in the prime mission. Prime is 5, with an expectation it would last for 10. And the primary limitation was the fuel, the hydrazine we used to stay in orbit, in our little tiny orbit around the L2 point. As I mentioned, with our terrific orbital insertion by the Ariane 5 rocket, we have enough fuel to go for 20 years. So, 5 years for sure. 10 is, on the books, but we could go another 10 after that.
And astronomy has a good track record of space telescopes lasting much longer, IRAS and other things. And Hubble's been up for 35 years, and it only had a 10-year original planned mission, right?
Right.
So,
Yeah. And if I remember correctly from the JWST stuff we were talking about at launch, the station keeping thrusters is the only real consumable on the station because the front is facing the sun that gathers all the energy and the instrumentation is facing deep space so that cools it. So there's really nothing else to run out.
No, there isn't anything else to run out. It's solar powered. We have solar
Yep.
arrays for power. And, it is out there in deep space and it is exposed to the space elements. There are micrometeoroids, and people probably know that the telescope has been hit by micrometeoroids, but this whole telescope is adjustable. And so if there's a whack on one of the mirrors, we can adjust the mirror. And that's done periodically we were going to do it every 2 weeks, but the mirrors have been so stable that I think it's now down to once a month. We go and we adjust the mirrors as need be. So,
That's phenomenal.
you never know. I mean, rocket science, we do it so well that people think it's easy, but it's not. If you get a cosmic ray strike in the wrong part of the electronics, a bad thing can happen. But, Hubble, like you said, Hubble's been up there 35 years. And other spacecraft, Voyager. Oh my gosh,
I know.
Voyager's been up there for even longer.
The fact that we can still get any signal from that far out in the solar system is just wonderful. And by the way, the KBO stuff, the chemistry of the KBOs or TNOs or whatever you want to call them, and being able to sort of pinpoint where in the volatility gradient they formed and seeing how they've mixed, that's just it's amazing science that we really did not expect we would be able to get.
Yeah, well, I think we kind of expected it. I mean,
I'm sure you did expect it, but those of us not in solar system.
Everybody wanted to do KBOs because they knew it would be cool. But I think the quality of the spectroscopy from JWST, I think, has really astounded all of us.
Yeah.
So I'm not only in my field, but in other fields. I mean, I was at one of the earliest JWST conferences, and they put up a spectrum of some distant, active galactic nuclei, and everybody in the audience is, so it's just like, it's amazing. Yeah, so it's going to be great. It's all, like I said, the threads are all starting to come together, and it's going to be really interesting. It's fun to be in a moment where all this is happening, and
so much is possible, right? Yeah.
All right. I remember just how far we've come even in a short period of time from the original raw images and like spectra that we were getting from JWST, even from then to now. It's worlds different, which is phenomenal in and of itself. All right, let me keep going so we can get some questions in.
Get some more.
Yep. So the comets that you mentioned that had water discovered on them, shouldn't the water have evaporated or bled off? And
yeah, so we're talking about main belt comets, and the question is, well, shouldn't the water be gone? The water often is locked into the surface. There are certain kinds of structures called clathrates, which can hold water inside their structures. And so what releases the water is a better question to ask than where is the water. And it could be collisions in the main belt with, small rocks hitting other things could release water. Yeah, it's these main belt comets are not like Comet Halley. They don't come in close to the sun, which tends to really heat up the surface and have a lot of water and then dust being spewed off of it. They stay out in the asteroid belt at that same distance. And so it's a different kind of beast. And that's why it was we expected there to be water and people couldn't see it until JWST. Now we can see it.
Right.
And that's because of the fidelity, because of the fact that we can see past just what is visually available like we could with Hubble, right?
It's the sensitivity and the wavelength ranges of JWST allow new observations to be made. Yeah.
Yeah, there are just so many molecules that show up in infrared that don't show up in optical.
Yeah.
Which
All right, next.
leads me directly to the next question, which is that fidelity available to us the reason we can get something like a distinguishable IR picture of Mars? Shouldn't the volcanic activity just make it like a super huge bright spot?
Volcanic activity on Mars. So
That
we
was
don't
the question.
Yeah. I think the question was actually about Io.
Oh, maybe it was IO. That's my fault.
Yes. So
okay.
the thing of the question, I mean, has JWST taken images of Io, and are they, like crazy because there's so much volcanic activity?
So yes and yes. We have indeed taken pictures of Io. There was 2 talks at the Paris conference about that, and it's riddled with volcanoes.
Yeah. I mean, if I remember my graduate school, there's like 7 volcanoes going off at any one time or something like that.
I think you're off by an order of magnitude.
Okay.
70.
70?
Yeah,
Okay.
I mean, in a single image, a single IO image, on one half of it, I mean, you could just like dot, 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 dot,
Yeah,
dot.
well, you can see the volcanoes, but I thought only like an order as a
If
7
you're seeing
were
them, they're
active.
hot. If you're
Are
seeing
they?
them, they're hot.
If they're seeing them, they're hot. Okay.
Yeah,
Well, I
and
mean, yeah.
some of them are very large, and I think maybe that's what you're thinking of, like Loki Patera and
Okay.
Kahana Healy. They are very, very big. They're the ones that Voyager saw. Voyager and I think New Horizons saw big plumes.
Yeah, the Tavashtar picture from New Horizons is amazing, right?
Yeah, but there are lots of other smaller volcanoes that are warm, and so
Okay.
it's a very, very active surface.
Okay, so totally covered with acne.
Well, yeah, it's kind of like, in Star Wars. You remember Anakin's world, that was all the lava everywhere.
Yes, exactly.
Yeah, kinda like yeah.
Was it Mustafar, I think?
Mustafar.
Yep.
Uh,
Has JWST coordinated with or have plans to coordinate with the Europa Clipper mission?
Oh, okay. So Europa Clipper, that's a mission that's on its way to the Jupiter system to study the planet Europa. It's not going to get there for a long time yet. And so right now, we're doing Europa observations with JWST, trying to map out activity. And I briefly flashed up a spectrum. There's one particular region, a chaos terrain on Europa, that we actually saw a carbon dioxide signature, a fresh carbon dioxide signature on there. I think that when Europa Clipper does get to the Jupiter system, and when the JUICE mission, which is another mission being sent by the European Space Agency, is also going to the Jupiter system, and it'll get there a little bit later, I think. We will, I'm sure, do some coordinated JWST observations because you always learn more when you coordinate. When you have multiple wavelengths and multiple looking at the same object, you learn more that way. So I'm sure we will do that.
NASA has a long history of doing these coordinated observations with New Horizons and Hubble, for example, tests finding candidates for JWST to study.
Absolutely.
It's
Cassini, we did a lot of Hubble Cassini observations. And we actually coordinate our telescopes as well. So we do coordinated Hubble and JWST. And we do coordinated Chandra and JWST, and ALMA and JWST, and ALMA and Hubble. Multi-wavelength astronomy is really how you get a more comprehensive study of whatever object you're looking at.
It's the coolest thing. It's just being able to look at these same objects in multiple wavelengths and learn totally new physics from each observation. All right, what else we got?
Okay. Was the reason that the Cassiopeia was not observed from Earth because of the dust clouds and ejecta?
Going all the way back to my
Yes.
intro,
Yes.
that's the thing. We really don't know why Cassiopeia A wasn't observed. There is a speculation that I forget who it was. 6 years later, saw a third magnitude star in a place that didn't exist. There's no star there today. So they're looking back at his records and going, maybe what he was seeing was Cassiopeia A. But yeah, the brightness of the flash. No, it's not embedded in dust. As far as I know, that would have stopped it. That's one of the reasons it's an interesting mystery.
Gotcha.
The good news for astronomers is that we're now building survey telescopes like the Rubin Observatory, the NSFDOE Rubin Observatory in Chile, and the Roman Space Telescope that will be mission ops from, science ops from Space Telescope, that are big survey telescopes of large swaths of sky repeatedly. And so when these things that pop off like that happen, we will have a much better chance of catching them now. It's going to be a whole new ball game when Rubin goes on sky later this year, and then Roman comes on a little bit later. We're all going to be
inundated with data from time domain astronomy.
Exactly. Yeah.
Roman is so exciting just by itself.
Yeah.
Okay, so let me pull another one here. Let me go back to the chat. Frank, if you have one in the meantime.
Let's see. My other thing, I think I've gotten through most of my things because they were things. I appreciated your story about pushing the limits of what the telescope can do in terms of slewing. People, are used to thinking of, oh, they can track things going across the sky. You can do that with ground-based telescopes, but space telescopes slew very, very slowly.
I tell you, props to the engineers, the engineering team. They went all out and delivered. And so they're the heroes of that story, that we got any data at all. It's great.
No, you've answered all the questions that I noted on there. There's a lot of stuff about Enceladus, and
Yes.
or the plumes from Enceladus. I don't see the questions right now, but it's always impossible to find them once you go back to the chat afterwards.
I wrote down a bunch. I just got through them quicker than I expected. Okay, so here's one. Are there ways to use different waveforms? And we know the answer to this, but if you could expand on it a little bit. Such as like sound, gravity, light, so on and so forth, to increase our resolution or to inform our actual images or spectra of distant solar objects? Because I know we use gravity lensing in some way with Hubble, but is there an equivalent to that for IR? Is there anything that we can do to push ourselves out further in that regard?
Well, the same concept of gravitational lensing, where you have a massive object that is distorting space and refocusing light from more distant objects, that works at all the wavelengths. And so we do gravitational lenses in the infrared as well as at visible wavelengths. And so that definitely is a tool for deep extragalactic work. Absolutely. And people have been talking about interesting ideas like using our sun as a gravitational lens to try to image distant exoplanets, right? That would require putting a telescope in exactly the right spot to line up with an exoplanet on the other side of the sun. Not impossible. but it would be a really niche instrument, we put it that way. You would,
Yeah.
extremely niche. One reason that we in the astronomy field tend to focus more on things like Habitable Worlds Observatory is that facility will not only do the habitable world part, but it will do amazing astrophysics, amazing solar system science, all kinds of other things in addition to the one niche thing. And so it's far more robust and just the bang for your buck. I mean, your return on investment is just huge when you build observatory class instruments.
Right. And these general purpose observatories have just proven their value over and over and over again.
I mean, people
Okay.
still want to use Hubble when it's 35 years old, right? Because
Yeah.
of course, it's been serviced a bunch of times, and
Yes.
we learn lessons from that. We talk about servicing for habitable worlds too. JWST is not serviceable, and so it is what it is, but it's great, and so it's robust, and
It's just working better than it was planned, which is
absolutely,
amazing. All
absolutely.
right, we got to stop it there because we're now at 90 minutes of our lecture, of our presentation, and that's been my usual cutoff on things. All right. So, next month, actually not next month. I'm always used to saying next month. Actually, in April, there will be another lecture. It will not be called a lecture. It'll have a new name. It'll be on a new YouTube channel. It will have a slightly different format. And there's one more thing I got to tell you. It will also have a new host. After 22 and a half years of hosting the public lecture series here at the Space Telescope Science Institute, this is my last one. I have decided that with all of these changes that we're going, it is better for me to step down and let somebody else, enthusiastic and new ideas and all fresh ideas, going to create this a new version of the public lecture series. When I took it over, it was called Open Night at the Institute. Okay, and I changed it into my vision of the public lecture series, and I've been doing that for 2 decades. But now it's time for somebody else to take over. Okay, so Heidi, I want to thank you for being such an amazing final speaker to send this out in a really way. And I want to thank all of the audience members, whether you've been watching a long time, we've had people that came to the Institute every month for decades, or whether you've just joined. It is a honor to have been able to spend 2 decades with you sharing the amazing science that we do at the Space Telescope Science Institute and in astronomy around the world. So thank you so much. Please keep watching, join our new YouTube channel, and really you're gonna still love the new version of this. And I will miss it, but I wish everybody the very best. All right, so thank you and good night, everybody.
Okay, we're good.
All righty.
Well, I'm